Suggest anything? Of course. So my first step is must be this. Without this step, I cannot differentiate. Because this is a function raised to a function, and we know there is no rule, no differentiation rule for that. Okay? So far so good? So now we differentiate the left and we differentiate the right. We have to be very careful with the right-hand side because it's a product of two functions, function 1 and function 2. So the right-hand side must turn into a sum. The left-hand side will be 1 over y times dy over dx. The right-hand side is sine prime, which is very good, cosine x times natural log x plus sine x times 1 over x. So you can put it in the denominator if you want to. I have to multiply by y, both sides. So then dy over dx equals x raised to sine x, and everything else, leave it alone in brackets. So this is cosine x natural log x plus sine x divided by x. And this is it. You don't have to do anything else. Just please remember, a function raised to a function has no formula. Our only way is to apply log and differentiate implicitly. Yes, please. Excellent question. Great question. Great question. Okay, let's talk about it. Thank you. Ready? We know that, so I would like to start actually with both. I would like to look at both exponential and log. So since the question is on log, let's start with log then. So when we differentiate natural log x, we get 1 over x. Also, when we differentiate a function that is inside log, this will be 1 over f times f prime. This should be times x prime, but x prime is 1. So this we know, correct? Now, let's say we want to differentiate something, another log, but this time log base a of x. What is the base in natural log? E. What is the base here? A. But it's not E. Because if it were E, I would have written natural log x. So it's not E. Here, A does not equal E. From our past experience with algebra, we know that there is something called the change of base formula for log. Change of base formula for log function. I don't have, in the old calculators, we did not have the option of putting the base in. So the calculators had only, I guess I was hungry, no. No. So the calculators have log and they have ln. But log with no base means base 10, and ln means base e. So this is what we had in the past. Now these more sophisticated calculators allow you to put the base you want. So in order to determine log base 6 or 5, we would use the change of base formula either into log, which is base 10, common log, or natural log. So it's natural log of the number over natural log of the previous base. And this is how we differentiate. So if you ask me differentiate this, I will say, okay, let me show you how to do it. Because I know that these two are the same. This is a number. I'm going to take it out. But then I differentiate natural log x, which is 1 over x. So if you apply, to answer your question, if you apply, it's okay. If you apply log base 10 to both sides, then the answer in the denominator has to be multiplied by natural log 10. So see, if A is E, then this is 1. Of course, the formula will extend if this is a function, right? So I have to be careful with that. So log base A of a function prime equals 1 over the function times natural log A, and of course times the function prime. The same thing when we differentiate e to the x prime. We know this is the nicest function on the planet. If I differentiate e to a function prime, I have e to that function times the function prime. But what if I don't have base e? The whole thing changes. So if I have a raised to x, this is a raised to x times natural log a. What if I have a raised to a function prime? Then I have a raised to that function times natural log a and times the inner function prime. Of course, if a is e, then you have the same thing as we had before. If this is e. But if it's any other number, and remember it cannot be anything else but between 0 or 1 or a number greater than 1. That's the base. Very good question, thank you. I was trying to find a way of inserting all this in, so great job. Okay, we're moving on to the next one. Any questions on the previous problem? Are we all comfortable with the first problem? We understand each step on the first problem. Yes, Matt? Everything okay? Everyone? Okay, we're working on the second problem. Working meaning with pencil and paper. Is it done? So the next problem is tangent cubed of sine x, and we want to differentiate this. Let me know when we have an answer. And I cannot stress enough, please redo the problems we did in class, please, in preparation for the test. Yes, ready? So it's 3 tangent squared of sine x times secant squared of sine x times, awesome, this is it. Do we understand this is the chain rule? There is no addition or subtraction in there. They're all products. Okay? So it's a function to the third power. We bring the power in front and we subtract 1 from the power. Then we differentiate the inner function, which is secant squared of the argument. And now finally we differentiate the argument, which is sine prime is cosine. Do we understand all steps? Yes? Okay. Do you think we can move on to the next one? Okay, sine inverse of 1 over x. Please be very careful with this function. If you don't like the way it's written, rewrite it as arc sine 1 over x. If you think you're going to be tempted to put negative 1 in front and subtract 1 from the power, which would be a tragedy, replace sine inverse with arc sine so you don't get confused. Because that is simply a notation, nothing else. Since I'm waiting for you, I'm going to take the attendance so I don't forget. Let me know if this is done. Is it done? Or we need more time? So remember, for the inverse trig functions, we only emphasized 3 of those, right? So arc sine prime is over the square root of 1 minus this squared, s1 over x squared, times the inner function prime. And if you remember, I asked you, please try to remember this. It's going to help us in chapter 5. If we understand that 1 over x prime is negative 1 over x squared, when we integrate negative 1 over x squared, you'll have no difficulties coming up with 1 over x, going backwards. Yes, I would try to simplify it a little bit, like negative 1 over, find the least common denominator, so x squared minus 1, and with this x squared in front. And when I take the square root and the square root, one of the x's will go away. So the answer will be 1 over x, the square root of x squared minus 1. You can say, am I happy with this? I'm happy with this. But I would recommend simplify it a little bit. If I said don't simplify it, then I'm happy with either one. Okay, are we moving on to the next one? And this is a product, sine x times the square root of 3x minus 1. Please make sure you finish up your work in WebAssign. Please. Okay, ready? For f prime, this is a product again. Function 1, function 2. Be careful. You have to end up with a sum of 2 products. Sine prime is cosine x times the square root of 3x minus 1 plus sine x times 1 over 2 the square root of 3x minus 1 but multiplied by 3. So I'm just going to rearrange it because I ran out of room. So this is cosine x the square root of 3x minus 1 plus 3 sine x over 2 the square root of 3x minus 1. And that's good enough. Do we agree with this? Any questions? Is this okay, everyone? Yes? Quinn, are you okay? This is okay? Everyone? Okay, moving on to the next one. This we cannot do just yet. Let's leave it alone because we haven't discussed the 3.11. So I need 10 minutes to present those functions. So we'll come back to this one. So let's look at G. We're given an equation. We're asked to use implicit differentiation of, obviously, x sine y equals natural log of x squared minus 2x and plus 4y cubed. So we're asked to find dy over dx. What does this mean, first of all? Automatically, they are telling us that y is a function of x. Very good. If you need help, I'll come over and help you. Just let me know, please. Okay, we need more time. Yes? Or can we start? We can start? Anyone needs more time? What will you tell me about the left-hand side? It's a product, very good. The first function prime, very good. Sine y plus x times cosine y times dy over dx. Do we all agree with the left-hand side? Now careful, this is not a product. This is a function by itself and another function by itself. So how do I differentiate natural log? 1. Very good. 1 over x squared minus 2x times 2x minus 2. 2x minus 2. I'm going to delete that. Good. Plus. So we have 12 indeed. So plus 12 y to the second times dy over dx. Do we all agree with this? And now remember, we are after this, but it's present in two different terms. And it happens that one is on the left-hand side and one is on the right-hand side. So I would like to move this term to the left, and I would like to move this term to the right. So then, we have x cosine y minus 12y squared dy over dx. When I move the terms, I also try to cut back a little bit, if possible, on writing. So this, when I moved it to the left-hand side, it becomes negative, and I factor out dy over dx. Then the right-hand side is 2x minus 2 over x squared minus 2x, and obviously minus sine y. So now dy over dx equals, this will be at the top, and this will be in the denominator. So 2x minus 2 over x squared minus 2x minus sine y over x cosine y minus 12y squared. And this is it. Did we all get the same thing? Yes? Everyone? Questions, please? Any doubts? You want me to go back to any of this? Is it okay? Okay, very good. So this, I expect you to fully simplify it. So we have y equals 2x minus 5 to the third divided by 3x plus 4 to the fourth power. It's a lot of work with this function. I don't recommend applying log. You can, if you like to do that, you can, and then simplify. I recommend to just use the quotient rule. Let me know if you need help. So use the quotient rule. The top function is number 1, the bottom function is number 2. Don't forget to square the denominator, right? The denominator would be 3x plus 4 to which power? 4 times 2. The 8th power. Yeah. Okay. And do not simplify in the sum. Make sure you factor first. Factor out first. I don't want to rush you, but I also don't want to waste time. So let me know when you need me to start. Are we ready? Yes? Okay, so then y prime, of course you can write dy over dx. The top function prime, 3 2x minus 5 squared times the inner function prime times 3x plus 4 to the fourth minus 2x minus 5 to the third times 4 3x plus 4 to the third, and of course I ran out of room, over 3x plus 4 to the 8th power. This will be a tragedy to simplify this with this. Please. So now we will completely factor the numerator. It has two factors. Both terms have two factors, 2x minus 5 and 3x plus 4. But now we have to talk about exponents, and also 2. 2 is a factor as well. So what is the exponent of 2x minus 5? I have to choose the smallest of the two. What is the exponent of 3x plus 4? I have to choose the smallest of the two. So let's see what is left. 2 is out. This is completely out, but there is a 3 left. And from those 4, I took out 3, so there is a 3x plus 4 left over. 4, I only took 2 out, so there is a 2 left in there. 3x plus 4 to the third is complete. And a 3. See? 2 times 3. Okay, so 3x plus 4 to the third is completely out. From these 3, 2 are out, so there is a 2x minus 5 left inside. Is this okay? Say it again? Yeah, I did, because it was up here, right? I should have done that. I just didn't see it because it was my fault. Sorry about that. Yes, I would factor out a 3 as well. So then I have 6. These 2 will do that. I can simplify factors. So 2x minus 5 squared over 3x plus 4 to the 5th power. Okay, so I have 3x plus 4 minus 2 times 2x and minus 2 times negative 5. So finally, this will be negative x plus 14, and I'll take it outside, of course. I want to use every inch, every square inch of this surface. I got to get myself into trouble. Okay, so final simplified form, negative 6, 2x minus 5 squared. And this was negative x plus 14, so x minus 14 over 3x plus 4 to the 5th power. Would we agree with this? Okay. Next time I'll bring another handout, or we'll choose other problems to work on. Yes, you changed the denominator into negative. Yeah, so you got the same answer. It doesn't matter, of course. Anything else? Or can we move on to this problem with the particle? Okay, let's do the limit first. We accomplished everything else. Let's do the limit and then the long problem with the particle. So let's work on limit as x approaches 0 from cosine 3x times sine 12x divided by 4x. When you plug in 0, what do you get? 0 over 0. However, I don't recommend L'Hopital's rule unless you say that this, when x approaches 0, where does this go? to 1. And then from here you can say limit as x approaches 0 from sine 12x over 4x. Yes, moving forward from here, you can apply L'Hopital's rule. But if you try to apply L'Hopital's rule on a product, it's going to take forever. Because it's always a sum of 2. And then you're left with another product, and then it's a sum of 4. And you don't want to do that. However, you could do the same thing like I did here with cosine later on after you apply L'Hopital's rule. So there are options. I would have not used L'Hopital's rule on this problem. I would have done this. So let's finish it with L'Hopital's rule. What would you say? This is limit as x approaches 0. If you apply L'Hopital's rule at the top, you get, yes, cosine 12x multiplied by 12. And the denominator prime will be 4. Where does this go when x approaches 0? 1. And how much is 12 over 4? 3. I would have done something else. From the very beginning, I would have presented this. I would have said limit as x approaches 0 from cosine 3x times sine 12x divided by 4x. But I know this is 12 and this is only 4, so I'll multiply top and bottom by 3. I can do that. If I multiply the top and the bottom by 3, then I know that this approaches, remember, 12x approaches 0. If x approaches 0, 12x approaches 0. And I have that little box. Where does this go? Excellent. Where does this go? It didn't change. Nothing changed there for cosine. Where does that go when x approaches 0? 1. The answer is, however, whatever you want, right? It doesn't matter. The method is not important as long as you know what you're doing. This is what I would have done. Because I need a 12. Inside sine, I can change anything. It's a 12. But here I only have a 4. So without multiplying by 3, I cannot say that this over this approaches 1. Because these have to be the same. And I only had 4, but I needed 12. There's nothing I can do inside the function. I can only manipulate something that is outside the function, sine. Okay, so let's read this problem. We had something similar in class. So a particle moves according to the law, so I'm going to copy that. So we have f of t equals negative 6t cubed plus 36t squared minus 54t. And now we have to answer, yeah, the temperature goes up and down. I have no idea why. It's warm and then it's cold and then it's a corner. Yeah. Okay, so we're asked to find the velocity at time t. So t is measured in seconds and s in meters. Okay, 1 minute. Let's talk about that. Can anyone give us the idea? How do I find the velocity? Yes. So f prime of t, can anyone give us the function? T squared plus 72t minus, very good. That's the answer to the first part. When is the particle, so let's find the velocity at time t, I'm sorry. And then when is the particle at rest? When v of t is 0, very good. So negative 18 t squared plus 72 t minus 54 equals 0. How many solutions do you expect? 2, because it's quadratic, very good. Of course, I'm going to try to simplify by at least negative 9 or negative 18. I refuse to solve a quadratic equation with a negative leading coefficient. So then I will have t squared minus, I think it's 4t, isn't it? And plus, is it a 3? It cleaned up very nicely. And then I'm hoping either use the quadratic formula, or I'm hoping that I can quickly factor and get the t's. So t minus 1 and t minus 3, so t equals 1 second and 3 seconds. It appears that this particle is at rest after 1 second and after 3 seconds. Okay. Find the total distance traveled by the particle during the first 6 seconds. What I would have to do now is, it is wise to determine when is the particle going in the positive direction and when it's the particle going in the negative direction. So t between 0 and 6 seconds, and v of t. And at 1 and 3 is 0 and 0. Remember, this is the velocity function. This is where we have to look. And I can factor out negative 18, and then I have that, right? T minus 1 and t minus 3. So that's the factor form and much easier to handle than that one. So if I plug in 0 here, obviously this is a negative number. So before rest at 1, it's negative. Then I can plug in 2, but it's easier to plug in 2 here. So 2 minus 1 is positive. 2 minus 3 is negative, but with negative in front, this is positive. And then beyond, between 3 and 6, you can plug in any number you want, like, I don't know, 6. 6 minus 1 positive, 6 minus 3 positive, but there is a minus in front, so that's why. So I'm getting it ready for the next page, right, where I'm going to add the acceleration in a minute. So the total distance then will be the absolute value of s of 1 minus s of 0, going in the negative direction, plus the absolute value of s of 3 minus s of 1. And finally, plus, can anyone give us the last plus? Plus what? S of 6 minus S of, all these numbers should be determined together. I will put the function in. Remember, this goes in the function. Oops, I didn't mean that. I meant this. So in y equals, clear if you have anything else, and put in negative 6x to the 3rd power, and then plus 36x squared, and then minus 54x. And second in table, and I want to plug in 0 and 1 and 3 and 6. And now, after you determine these numbers, put them in the formula for the total distance. So we have s of 1, negative 24 minus 0, plus the absolute value of s of 3, which is 0, minus negative 24. And then finally, plus negative 324 minus s of 3, which is 0. So this is what I got. So I have 24 plus 24 plus 324. So 24 plus 24 is 48, and the 48 here will mean 2 and 1, 7 and 3. And this is in feet. Let me look again. Was it in? No, it was in meters. Sorry, I should have looked before writing. That's the wise thing to do. So then the particle covers 374 meters in the first 6 seconds. Find the acceleration at time t and when the velocity is 0. So let's work on the acceleration. And we know when the velocity is 0. When is the velocity 0? At 1 and 3. So we have to find a of t, and then we have to find a of 1, and we have to find a of 3. So we found the positive direction and the negative direction. Now we have to put it together and find when it's slowing down and when it's speeding up. And that will be the end of this handout. No, we still have the hyperbolic functions. One example. Can anyone give us the acceleration function, which is the derivative of the velocity or the second derivative of the distance or the motion? Yes, negative 36t plus 72. So we have to plug in 1, so f of 1 will be 36. Measurement unit. Very good, meters per second squared. Excellent. And then with negative 3 minus 72 will be negative 36, which makes sense. It's only the direction. We know that. And when is the acceleration 0? At t equals 72 over 36, which is 2 seconds. Would you agree? Negative 36 times 2 plus 72 is 0. So we have to put in the table. So at 2, it's 0. It's a linear function with a negative slope. What is the sign before 2? If it has a negative slope? Positive and then negative. So now let's identify what happens here. Between 0 and 1, between 1 and 2, between 2 and 3, and between 3 and 4. 3 and 6. Between 0 and 1, the velocity and the acceleration do not work well together. Their forces are against each other. So what does the particle do? Slowing down. There is an n in here. Okay. Now here, between second 1 and second 2, both of them have the same direction. They're helping one another. What does the particle do? Speeding up. Between second 2 and second 3, one of them is positive and the other one is negative. They don't work well together. What does the particle do? Slowing down. And between 3 and 6, both of them are in the same direction. They're helping one another, so the particle is speeding up. Any questions? Sorry, I didn't mean to take it. Any questions? So what I would like to do now is talk about the hyperbolic functions. There are 6 hyperbolic functions. There are 6 inverse hyperbolic functions, and of course each and every one of them has a derivative. I only want one minor effort from you. So 3.11, hyperbolic functions. I only want 3 of those. Not even their inverses. Just 3 of those and their derivatives. So first of all, I'm sure you're wondering probably, listen, do I really need more functions? Do we really need more functions? Yes. And here's an example. You still see, even today, I mean, this is going on for a long time, right? So we have poles like and a cable or telephone or power lines between 2 poles, correct? Well, they were confronted with something like this, and they went to mathematicians, and they said, well, give me a function, because I need to have something that has this length and has this curvature. Come up with a function, and they did. No function works well here. Not trig, not polynomial, not rational, not radical, not absolute value, nothing. And they came up with a function that combines the 2 exponential functions. And they came up with this. Also, they wanted to model the ocean waves. And they said, well, what about sine and cosine? No. And they came up with another combination of exponential functions. Not any exponential function, but the natural exponential function. So then I did not see the gate arch in San Luis. I only saw pictures of it. I've never set foot in San Luis. But the way they calculated and they put all the pieces together, it's a hyperbolic cosine function. Nothing else worked for the model that they were looking at. So finally, what is going on? So what are these hyperbolic functions? 6 of them. I only need 3. I just want you to have an idea. So here's one. Hyperbolic sine. Here's the next one. What do you think? Right. Hyperbolic cosine. And the very last that I need, so you at least remember these 3. What do you think it's going to be? Right. That's all I want. And you can say, oh, but these look like trig functions. They're not. Why they used sine hyperbolic, cosine hyperbolic, and tangent hyperbolic is because the relationship is fantastic. Who came up with this? The relationships between these 3 functions and the other 3 and their inverses is very similar to the relationships between trig functions. These are not trig functions. However, the relationships between them is very similar, or are very similar to the relationships between trig functions. So I was just saying that they are combinations of natural exponential functions, but I have to show you. So here is hyperbolic sine. E to the x minus e to negative x divided by 2. A combination of 2 natural exponential functions. And hyperbolic cosine, what do you think the difference will be? Instead of plus, the minus is plus. And yes, this is the function they used for this. It can have some transformations on it, on some different coefficients. It doesn't matter, but it's the base function is a hyperbolic cosine function. Upside down, of course, here. Upside down. Okay. So what do you think hyperbolic tangent is? F of x equals hyperbolic tangent. What do you think this is? Of course, it's sine x, hyperbolic sine x over hyperbolic cosine, and it's this over this. So e to the x minus e to negative x, e to the x plus e to negative x. If you want to square sine hyperbolic, square sine, and square cosine, you will see the relationship is very similar to sine squared plus cosine squared from the pure trig functions. And other relations are very similar as well. But now let's talk about hyperbolic sine prime. No, we're not going to use a definition, I promise. But let's use the differentiation rules on either sine or cosine. It's up to you, or both. So in order to differentiate this, I have to differentiate that. Well, I put 1/2 in front. So when I differentiate e to the x, what do I get? Very good. And then when I differentiate e to negative x, be very careful because the power is not plain x. So I have to differentiate as an inner function. So it'll be negative e to negative x with minus in front. But what is this? It's hyperbolic cosine, right? So this is hyperbolic cosine x. I'm assuming that initially they didn't call them that. They said, okay, we're looking at e to the x minus e to negative x when they couldn't find a name. And then when they realized that one is a derivative of the other and vice versa, they said, oh, the hell, we've looked at something like that, similar functions. Yeah, why don't we call them something with sine? And they just punched in the sine in there. Okay, what do you think cosine prime will be? Hyperbolic cosine prime. And no, it does not have the minus in front. You may have not expected that, but it does not. It's just plain sine. So hyperbolic sine prime is hyperbolic cosine, and vice versa, hyperbolic cosine is hyperbolic sine. Prime is hyperbolic sine. And of course, no secret there. Hyperbolic tangent prime is the same thing as we know it from the trig functions, which is, yes, secant square. I remember 2 has to be after h. Sorry about that, I rushed. So it's hyperbolic secant squared of x, of course. Let's also look at, since I mentioned that, let's look at the relationship of hyperbolic sine squared plus hyperbolic cosine squared, which is, I take 1/4 outside, e to the x minus e to negative x squared plus e to the x plus e to negative x squared. So at least we look at one relationship between hyperbolic sine and hyperbolic cosine. When we square binomial, like these two, sort of binomial, two quantities added together, how many terms do I get? Yes, of course, thank you. So this is 1/4. The first term squared, e to 2x minus 2 times the first times the second, but when I multiply these two, I get 1. Copy the base, add the exponents. So it's minus 2 and plus e to negative 2x. Same thing here, plus e to 2x and plus 2 plus e to negative 2x. And you see what happens? There are 2 of those and 2 of those. So I have 1/2 e to 2x plus e to negative 2x. Any questions here? Any questions? So let's look at if there is another way of writing this. So what I did was I factored out 2, and I simplified with a 2 from both of them. But now I would like to take it one more step further. So this piece is this, and this piece is this. It just has that minus 2 in there. So is there anything we can do here? Any simplification? If I change this piece into e to the x plus e to negative x squared, this one has a 2 and minus 2.
I'm sorry, minus 2 comes again?
Because when I square this, I will have e to negative 2x, e to 2x plus.
No, I mean the minus. I'm sorry, go ahead.
Yes, plus 2 times the first times the second, which will be the plus 2. And plus e to negative 2x and minus 2. Right? Because I have to add and subtract 2 in order to be able to complete the square. Does it make sense? So here I already have a 2. Minus the 2, I will get back this. Okay, I'm just trying to see if I can further simplify this, which will be e to the x plus e to negative x, everything squared. You don't have to write this. I'm just minus 1. And what do I get now? So this is e to the x minus e to negative x squared divided by 2, right? I'm thinking if I can further simplify this somehow. And this is the square root. So this will be cosine squared over 2 minus 1, right? Because cosine, yes, so cosine, so this piece is 2 times cosine. Am I getting anywhere with that? So 2 times cosine hyperbolic squared divided by 2. So I get 4 divided by 2, so 2 hyperbolic cosine minus 1. All these functions have very similar identities with the trig functions. Very similar. Okay, so let's look at differentiating a few functions. Please choose if you'd like on page 263. Let's say 30 to 45. But please select, otherwise we'll have to use formulas, which is fine by me. But please select, if you can, sine, hyperbolic cosine, hyperbolic tangent. Let me select the first one, and then you'll select the next. What about 33? In 33, we have hyperbolic sine, natural log of hyperbolic cosine. So then we saw what the sum of the squares of the hyperbolic sine and cosine equals to. And then we're going to look at the difference also. So we are asked to differentiate. So h prime will be, what will you write?